Okay, quiet please. We're going to get going. This is going to be your review, right? If you take a test question and don't even follow the directions on the test question, you start doing something you remember we did once in homework, right? I'm telling you, we're going through this right now, and you're getting the exact idea of what kind of things you're expected to do on the test, right? And there'll be a video of it too. You could even go back as you're going through the study guide. Make sure that you're doing what is expected from you here, right? Some of this is going to be reviewed because we always go back a little bit, especially they're all worked up about us solving equations. So the kind of equations that we've solved in the past so far don't account for much, but the absolute value, a little bit. So we're going to go back. There's like 3 problems like that. And these are just examples already worked out. I'm just going to explain them and move on to the next. There will be some later that we end up having to do more work on. But remember how we solve an absolute value equation, right? Right? First you isolate it, right? In this case, the absolute value is isolated. It's the only thing on its side of the equal sign, right? Then you break it down, right? You write 2 equations. And one of them, what's inside the absolute value equals the right-hand side. 2x minus 1 equals 5. No absolute value symbols. It is wrong for you to, at that step, write absolute value symbols. There are none, right? And then you say, or, and you set what's inside the absolute value equal to the opposite of the right-hand side. Okay, so that's 2x minus 1 equals negative 5, right? Because if either one of those things is true, 2x minus 1 equals 5 or negative 5, when you take absolute values, they equal 5. So the equation is satisfied. So you solve these 2 equations. Those are very basic algebra equations. And you get your 2 answers. Okay, and you can definitely check them. Right, this is an example in the book near the study guide problems. I don't want you copying down every word that you see on the slide. Right? And for one thing, all these things will just look in the book. Now, it's a slightly different problem if the absolute value equation has variables that are inside the absolute value and outside the absolute value. When you get those kinds of problems, then you're going to see the kind of directions that say at the end, check for extraneous solutions. Okay, so you go through the same process, right? I'm setting what's inside the absolute value equal to the right-hand side and the opposite of the right-hand side, right? Meaning, take that 4x plus 5, which you don't actually know what the value is because it's got a variable in it, and put a minus in front of it. And then from there, you can distribute the minus to get negative 4x minus 5. I mean, you may or may not show that step. You may just say equals 4x plus 5 equals negative 4x minus 5. That's fine, right? But you do need to make sure that they are both negative. They both change signs. Okay. And you solve them. You know, just using basic algebra, you solve them. But what you notice when you solve these kinds of equations, one of those solutions likely won't check. Right? In this one in particular, if you put in negative 3 for x here, right, not in one of these equations here, we're talking in the original equation, if you put in negative 3 there and there, and you simplify each side, you get that the absolute value of negative 7 equals negative 7. And that's not true, right? It equals 7. So this one doesn't check extraneous. Okay, this one checks. Absolute value negative 1 is 1. Okay, there will be an absolute value less than, right? Not a greater than, right? Not a greater than, just a less than. Right? So first step, as always, isolate. If it's already isolated, then you got to break it down so that there's no absolute value symbols. Do you remember what you do for an absolute value less than? You write a three-part inequality, right? What does that look like? Now, don't tell me a number. What number? Look at this problem and tell me what number should I write first? -5. -5 is less than 2x minus 1 is less than 5. Right? It's telling you that that variable expression is in between. Its values are in between -5 and 5. Anywhere in the middle of that is okay. Right? How do you solve a three-part inequality? You solve for the variable in the middle, right? So you're isolating the variable that's in the middle section of the three-part inequality. So in this case, add 1. -4 is less than 2x is less than 6. Divide by 2. So -2 is less than x is less than 3. Is somebody saying something? Speak up. How do you graph that? Right, do you have open or closed circle? Because it's not or equal to. So that means that -2 and 3 are not part of the solution. Right? And then you have to say, well, where's the shading go? Well, again, you should be looking at three-part inequalities as between, right? The shading goes between -2 on the left and 3 on the right. So the shading is here. Okay, write an equation of an absolute value function based on looking at a graph. So in this one, remember, absolute value equations look something like this. It means you've got a variable inside the absolute value. Okay, the question is, how do you shift that v by adding or subtracting numbers inside the absolute value and after the absolute value? So in this case, it looks like we've gone left 2, down 3. How do you make it go left 2? Plus 2 inside and minus 3 after. Right? How about the next one? Right? It's right 2, down 3. So in order to make the function go to the right, you go minus 2, minus 3. Okay, how about this one? This one right here. Okay, so it's right 2, up 3. Minus 2, plus 3. And then the last one. Right, it's left 2, up 3. Right. How would I make, let's say, this one right here, open down? Yeah. What is it makes it go down? A negative in front. So you should know how these things go. Up, down, left, right, and flip. If that's the way you want to think about it. Okay, then we get into the chapter 6 stuff, like the first 2 questions on the quiz. Put a polynomial in standard form, classify. Okay? In this case, what did you have to do to classify, to go from, or sorry, to put in standard form, go from here to here? Put the highest degree term on the left, right? And then it goes down, right there. X squared, x to the first, constant. Okay? And you classify it. By degree, you would say squared means quadratic. By number of terms, 3 terms means trinomial, right? How about this one? What did they have to do to this one before they put it in order? They combined like terms, right? These 2 had to be combined. And then they put it in order. X to the 4th. 10x squared minus 6x squared is 4x squared plus 4x minus 12, right? And that is 4th degree, so it's called quartic. And 4 terms means polynomial, right? So what are the other terms for, let's say, for degree? First degree is linear. Second degree is quadratic. Third degree is cubic. 4th degree is quartic. 5th degree is quintic, right? Number of terms. 1 term is monomial. 2 terms is binomial. 3 terms is, and polynomial means 4 and above, right? What about a constant? What is a constant function? Without a variable, right? Something like 7. I mean, that's a polynomial. It's a constant. What's the degree of that? 0, right? Remember, linear is like 2x plus 1. Because the x is raised to the first power, it's linear. This doesn't have an x in it. Another way to think of it is like this. It's got x to the 0 power, but anything to the 0 power is 1, the number 1, right? That's why you don't see it. Okay, so a constant is a 0 degree function. Okay, modeling data with the calculator, like we did on the 3rd question. This one comes from the textbook. You know, I used to have a job working on dairy farms, so I had to show this. So they said find a linear function that approximates this data, right? The 3 data points are, this is the amount of milk production. Not even sure they give us the unit. Oh, milk production in billions of pounds. So in 1955, it was 16.5 billion pounds. In 1980, 22.4. In 2005, 22.9. So how do we model that? Stat, edit, right? When you get to the stat edit screen, you see your L1 and your L2, and you put your X values under L1 and your Y values under L2. Right. Now, notice that they didn't put in the L1. They didn't put in 1955 and 1980 and 2005. They put in 55 and 80 and 105, which is fairly common. When years are your independent variable, they usually say there's a 0 year that's closer to your period of time you're dealing with. So you could say these are the years since 1900, 55, 80, 105. So you put those data points in the calculator, and then how do you make the linear equation since they told you what to use? Stat calc 4 for linear. And you would see these coefficients here, right? 0.128x plus 10.36. You won't see what they've got here. Don't worry about that. And then they drew their line in the middle of the data. Do those 3 points look like linear was the best approximation? No. But remember, how many points does it take to make a line? 2. So whenever you've got more than 2, especially if you only have 3 points, unless they all happen to fall exactly on the same line, it's going to look like probably a quadratic is a little bit better. That there would be some kind of a curved function that would be a better approximation for them. Now, so let's say you go through and you say, with the same data, let's make the quadratic and see what that one looks like. Then you get this. Using their same data, this is the quadratic regression equation. And this is what it looks like. And, you know, because how many points does it take to make a parabola? It takes 2 to make a line. So how many does it make? 3. So that means there's only one parabola that could go through those 3 points. And it does definitely go through those 3 points, right? Boom. But look at that shape of graph. Does that look like a reasonable curve for milk production since 1900? It started at 0. It went up, reached a peak, and then went down back to 0. You know, even though that probably is a better fit for the 3 points, that's probably not the best model. It's probably more like this. I would say it's probably not even this. It's probably more like milk production increased up to a certain point like that. I'll bet you it's more like leveled off. Because people don't drink as much milk as they used to. We used to drink a lot of milk. Back in the early 1900s, you know, it was really emphasized. It was called nature's most nearly perfect food. And, you know, they tried to get people milk because it was seen as a good supply of nutrients and calories and things like that. And then, you know, it became very important that it was clean. So having a clean, plentiful milk supply was a big deal. And the supply of milk did go up pretty much. But then, you know, 30 years ago or so, we started getting all this kind of skim milk and 2% milk. And if that was the only kind of milk you ever drank, you know, you probably don't know what it is. It tastes good, cold, whole milk, fresh from the cow. Okay. So remember, you have options. You have options to make models of data, right? We go to this menu right here. And what are we looking for? For a linear, we're looking for data that looks like it could be approximated by a straight line. Okay. For a quadratic, that's linear. For a quadratic, it should look like it's got a U shape to it, parabola. Right? What does a cubic look like? How many turning points in a cubic? 2. Remember, it's always 1 less than the degree. That's why like a quadratic is second degree. And how many turning points does it have? 1. A linear is first degree. And how many turning points does it have? 0. A cubic is third degree. It has 2 turning points. And a quartic, you know, a quartic could be 1, 2, 3. 1, 2, 3. So we should know those, at least those basic shapes. Okay. Where do you look for on a graph of a polynomial function for the zeros? Mark. Where it touches the x-axis, right? So like in this case here, there's zeros here. And you should be able to estimate them, you know, just by looking at them. What does it look like they are? -3, 0, and 3. Okay? There is a test question. There's a graph, and it's that easy. It's that easy. Just look at it. If you know what zeros are, you'll be able to read them right off the graph. Right? Do you remember what did we mean by the end behavior of a graph? Where? At the ends, right? It means what's the graph doing as you go towards x equals negative infinity or x equals positive infinity? This one, what's it doing as x goes towards negative infinity? It's going down, right? And then on the right side, it's going up. Okay. So if you're going to say it in order, just say down, then up, down, up. Right? What would you say about this one? Up and up. What would you say about this one? Down, then up. And the last one? Down and down. Okay, and then the last thing that we did with this, I mean, I think that there's three questions referring to one graph. The first question is, what are the zeros? That should be an easy question. Second question is, what's the end behavior? That should be an easy question. The third question is, what are the intervals of increasing and decreasing? And that's usually a harder question. Okay, let's see, we're there, it's red. So, for example, what do we mean by increasing and decreasing? You know, if this is increasing because the graph is going up from left to right, right? It's decreasing here because it's going down from left to right, and then it's increasing. So the turning point is where it changes direction. There, and there. Right, and here, it changes direction, changes direction, changes direction. Right, how do we remember, when you ask for intervals of increasing and decreasing, it means intervals of x, right, x values. You don't want to say the y values, you want to say intervals of x. So how do you describe this interval that starts at the left side of the graph and goes all the way up to where the graph has a turning point? Right? What is the value of x right there? It's actually -1. So how would you describe that interval? X is less than -1. Increasing. That's the interval. Okay. How would you describe this interval of increasing? It's starting at which x value? It's starting at 1, and it goes infinitely to the right. So you say increasing, x greater than 1. And then how do you describe the interval of decreasing, which is in between -1 and 1? You use a three-part inequality, right? That's how you say in between. Use the three-part inequality. So we'll say it's decreasing. Decreasing, -1 is less than x is less than 1. In between those two values, it's going down. Okay. There will be a question like this. It is not, you don't have to factor it. It's already factored. But you have to be able to say, looking at the factored form of the polynomial function, what are the zeros? What's the multiplicity? What are the zeros? Okay, the zero that comes from the x squared is 0. And from x plus 2, -2. And from x minus 4, 4. Right, so if I'm going to write those zeros, right, I'm going to write them like this. 0, -2, and 4. How do I include the multiplicity? You know, which one has a multiplicity? The 0 has a multiplicity because of that exponent. So you would say 0, and then in parentheses say mult2. Or you could spell it out if you want. But make sure it does not apply. It does not apply to the -2 and the 4. You know, a comment at the end of the line that just says multiplicity 2 won't get you credit for that. It's got to be specific to the 0. Okay, now, why do we care about the multiplicity? Because of the effect on the graph. Right? We expect a different behavior when the 0 is there once than when the 0 is there twice. Right? Notice at -2, the graph the x goes right through the x-axis at the x-intercept. Same thing at 4, goes right through the x-axis. Right? But for the 0 mult2, look what it does. from beneath, it touches the x-axis at x equals 0, and then it goes back in the same direction. So when you're looking at a graph and you see that behavior, you know that it's there, not just twice. It could be there any even number of times, not an odd number of times. Most of the time, it's 2. Right? How do we turn zeros into polynomials? Well, we kind of just did this, didn't we? We did it over there, right? We turned it into the same thing. So take the zeros, right? Turn them into linear factors by doing x minus the 0. So negative 2 turns into x plus 2, and it's there twice. And then 2 turns into x minus 2, 3 turns into x minus 3. And now this one is a little more difficult because it has so many zeros, right? So now you have to multiply. And how do we do that? How do we multiply 4 binomials together? Choose 2 to go first, and then you do another 2. Now, when you get 4, there may be something smart to do that kind of is going to save you a little bit of work. Does anybody think of 2 of these factors that actually would multiply together? To say again? X plus 2, x plus 2? No? What kind of factoring do we call that? X plus 2 times x minus 2. What's the pattern that factors like that? Say again, Lee? Difference of squares, right? So we know we can FOIL this, but we know what that's going to be. That's going to be x squared minus 4. So it probably makes sense to multiply those together because now we don't get a trinomial. That's going to make our multiplying the last step pretty hard, right? So we actually just get a binomial. And now we can do these other 2 themselves, right? X plus 2 times x minus 3. So let's do that. X plus 2 times x minus 3, right? That should be x squared minus x minus 6. Okay, now how can I multiply this binomial times this trinomial? Do a little grid, right? Do a little grid. I mean, there will be times when you can't avoid having a trinomial times a trinomial. It happens, right? But in this case, there was no reason that we had to do that. We could make it a binomial times a trinomial. So on the left, we've got x squared minus 4. On the top, we've got x squared minus x minus 6. Right? And now we're going to fill in every square in the grid. X squared times x squared. X to the 4th. X squared times negative x. Negative x to the 3rd. X squared times negative 6. Okay, negative 4 times x squared. Negative 4x squared. Negative 4 times negative x. Positive 4x. Right? And then negative 4 times negative 6, 24. So you could see the x to the 4th is here. The x to the 3rd term is, there was only one of those, that's there. The x squareds, there was 2 of them. Negative 4x squared minus 6x squared. There's the negative 10x squared. The 4x and 24. 4x, 24. So be able to do that. Right? Sum and difference of cubes. Right? We got formulas. Yes, you have to know the formulas. They're not given to you. You have to know them. Right? Remember the pattern. Right? The sum of cubes, a to the 3rd plus b to the 3rd, is a plus b times a squared minus ab plus b squared. Right? The difference of cubes is almost the same. Right? It's got more things similar than it does different. Right? That plus is a minus. That minus is a plus. Everything else is the same. So notice that if it's the sum of cubes, what's in the first set of parentheses is the sum, right? If it's a difference of cubes, what's in the first set of parentheses? It's a minus. And then it's the next sign which switches. So that's what you need to keep straight. Okay, now these are solving equations. They're not just factoring, they're solving equations. I think on the test, there's one that is a pure factor, and there's another where it does come up an equation which is the sum or difference of cubes. But if you're paying attention to this, you'll have heard the answer, right? Okay, so let's see. Let's factor this using the formula. That'll be x plus 4 times x squared minus 4x plus 16. So remember, we factor it so that we can use zero product property. Right now, by the zero product property, what value of x is going to make that factor equal 0? Negative 4. So we got that one. That's always the easy one. That's always the real number. Right? X equals negative 4. Now we got to solve this one. What values of x make that equal to 0? And how are we going to figure that out? It's always the quadratic formula. Because always what kind of answers are you going to get from that? Imaginary. They're always imaginary. Always. Okay. Remember, we expect that because this is a cubic, that we could have 3 complex solutions. Some can be real, some can be imaginary, and we just found we got 1 real, and then we'll get 2 imaginary from this, which adds up. That's what we need. So let's see. Here we go. This is x equals negative 4 plus or minus the square root of negative 4 squared minus 4 times 1 times 16. X equals 4 plus or minus the square root 16 minus 64. Okay. Again, don't turn it into a decimal. Simplify the radical. Is 48 a perfect square? No. Does it have any factors that are perfect squares? What is the biggest factor of 48 that is a perfect square? 16. This was a homework problem. We've already done this, right? 48 is 16 times 3. So the square root of 48 is the square root of 16 times the square root of 3. And the square root of 16, we know, that's 4. Now, the fact that it's negative 48 means that's a negative, that's a negative, and when you take the square root of a negative, you get I. Right, so this is 4 plus or minus 4i times the square root of 3 over 2, which is 2 plus or minus 2i over 3. So mainly, you're going to have to just try to remember the formulas. Figure out a way to remember them. Okay, solve an equation, what I was calling in class a GCF plus. Right? There's going to be a greatest common factor, right? What is it? Well, first remember, you had to get everything on one side, 0 on the other, and then the greatest common factor was x. Now this 2x squared minus 5x minus 3, okay, you have to think, is it factorable? Meaning, are there factors of 2 times negative 3, negative 6, that add up to negative 5? Yes. Negative 6 plus 1. Okay. Again, remember, for this you go 2 times negative 3 is negative 6. The factors of negative 6 that add up to negative 5 are negative 6 plus 1. Now, they have skipped 2 or 3 steps, depending on how you write it, to get from here to here. But remember how we do that. We go 2x squared minus 6x plus x minus 3. We group the first 2, we group the last 2, and then we do greatest common factor on this set of parentheses. 2x times x minus 3 plus x minus 3. And then the last step of that factoring gets you to here. 2x plus 1 times x minus 3. And then you still got the x in front. So now, in factored form, boom, boom, boom. What are the zeros? 0? Yeah. 0 and 3, those you should be able to get immediately. If you have trouble with this 2x plus 1, make an equation out of it, solve. It's negative 1/2, right? If you put a negative 1 over 2, the 2's cancel, and negative 1 plus 1 is 0. So there's your three answers: 0, negative 1/2, and 3. Okay, find all the real zeros using a calculator. So remember, when you find the x-intercepts, those are the real zeros, right? The imaginary zeros don't show up on the calculator. So we need to put this in the calculator. So I go to the y equals and put in that function, x to the third minus x squared minus 7x plus 7. And look and see what you see. How many real zeros do you see? 3. Remember, it's a cubic, so how many could you see? The maximum you could see is 3, and they're all right there. 1, 2, 3. So remember, if you can find them in the table of values, definitely look in the table of values. Does it look like any of these might be right at an integer value that's in the table of values? I mean, that one right there looks like it's at 1. How can you verify? Yeah, above the graph, that's table. So you go second graph. And you look, at x equals 1, what is the value of y? 0. So there's one answer. Okay. Now, the other two are clearly not going to an integer value. They weren't in the table of values, and they look like they're not going to an integer value. So here's where you got to remember that process we did last time, right? Do you remember, how do we find the zeros using the calculator? Second, trace, right? And then what are you looking for in that menu? 0. Number 2 is 0, right? Now let's say we're looking for this 0, the one on the left. Right? When it asks for left bound, what is it asking for? It wants an x value which is to the left of that 0. So you can estimate it on the screen, right? What's a good value over here? Just make sure, like if you said negative 20, you're going to get an error because that's not on the screen. It's got to be on the screen. How about negative 4? Right, that's a negative 4. So when you hit enter, now it's going to ask for a right bound, which is an x value which is to the right of that 0. Not too far over, but how about in between that 0 and the origin? Pick a value. Negative 1? Okay, so say negative 1. And then it always, when it says guess, you always hit enter. Right? So when you hit enter, the cursor should jump right to the 0, and there's your value. I don't even know where you can. You know, it's a question mark guess. It's like, what are my options here? You only have one. Guess. Okay, so try to find this one. See if you could use the calculator to find the one on the right. This one was negative 2.65. See if you can find the one here. Who's got it? Is it Rebecca? Okay. Essentially this number, but without a negative sign, right? Okay. So you should be getting, and again, here, remember, here's another way you can do that left bound, right bound stuff, right? You can go second, trace, 2, and then instead of having to enter x values, you can move the cursor with the arrow keys. Like if I want to find that 0, I got to use the right arrow to get that cursor, and it's following along the function. I got to get it along. Let me get past the second 0. Okay, now it's to the left of this 0. Enter. Okay, for the right bound, if it says right bound, you can use your right arrow to get on the other side of the x-axis. Watch it go. There you go. So that's the right bound. And now you want to guess? Of course. 2.6457. Either way works. Okay, remember how we came up with the number of complex zeros, the possible number of imaginary and real zeros? These are the same problems we did for homework, and we're not doing the possible rational zeros for roots. Let's say we do number 27. Right? How do you determine the number of complex zeros? Okay, we got a word for that. What is the highest, what do we call the highest power of the term? It's called the degree, right? So the number of complex solutions is 5. Okay. The possible number of imaginary, there's like one fact that we use for this. What do we know about imaginary zeros or roots? They're always an even number of them because, again, where do they come from? Quadratic formula, right? They're coming from after the plus and minus. That's where the I comes from. So if it's going to have both a plus and a minus, that's an even number. So when you want to know the possible number of imaginary, you got to think of what are all the even numbers less than or equal to 5? 0, 2, and 4. Okay, so the possible number of real we know that the number of real zeros plus the number of imaginary have to add up to the complex. So if there's no imaginary, how many real are there? 5. Right? If there's 2 imaginary, how many real? 3. And if there's 4 imaginary, how many real? 1. Right? So these have to add up to 5. Clear as mud? Okay. Okay. Before I go to that, right? I mean, first I want you to see this, right? I'm going to send out the study guide. The study guide is not just the list of pages and problems, but it's also saying this is what you're supposed to be getting out of them. Okay, so it's clear. And if you just look at that, what I find is that there may be like aspects of the problem which I'm not really interested in, but it's the only thing I can really get you to do something with. And you're going to spend your time doing things that really are not what I'm going to ask you. So you should be using that to make sure that you're focused on the right thing. Now, there's a couple of things in here that you can't take the calculator home, so you can't really practice on that. But we will do it again before we start the test on Wednesday. And that would be the calculator things are here and here, right? Modeling data and finding zeros. Right? Those are things that you can't do at home unless you got your own calculator. So we'll do it right before the test to remind you. So I'll leave that up, and then after, if people have finished copying, if you want to, because I'm going to email all this stuff, it'll be on the website. Then I'll put up that other page if you want.